Disconnected. Hi, Lydia. Oh, you're good. Alright, should be good to go. Okay. Yay. Alright. Alright, let me share my screen. Okay. Welcome back. Good to see you. How was break? It's okay. Hopefully got a little bit of relaxing, had a little bit of fun. Stayed out of trouble. That's always good. I'm glad you're back. So yesterday, hopefully it went okay for you. Reading back through some complex number stuff, where you should have seen most of it before. But I wanted to take today. I looked through the classwork and it looked pretty good. Of course, the answers were sitting right there. So I want to make sure that a couple things that they talk about are solid, and there's also a couple things that they don't mention that I want to make sure that I kind of supplement and fill in. And then I just want to give you a chance to make sure you got it in practice, and we'll call it homework 2.4 because cohort A is at home doing it. So I might as well give you the chance to do it right here in class, so you can get those points. And we'll spend really just the first, I don't know, a little while going over a couple things. And then, but the rest of the time, I'll just put up a copy of the textbook and I'll pick out a handful of problems and just make sure you can do it. And then 2.4 is going to be done one day. That's all we really need. And we'll start 2.5 tomorrow. Now, it's a brand new thing that I really don't think you know a lot about. So if you could, I'd like you to join live or at least watch the recording tomorrow rather than having you read through the textbook and do it, because that is as much fun as it sounds. So let's do this. Let's let me touch on a couple of things. Take out something to write with, something to write on. I'm going to start over here and just kind of fill in some gaps, make sure that what you think you know, you actually know. I'll try to stay above Jacob's head so he's not in the way. Yeah, get low. There you go. No, you're good. With 2.4. Okay, so 2.4 complex numbers. Okay, and I know you saw this stuff last year, so I just want to make sure that how you feel about this when you walk out of today is 100% confident that if I gave you any kind of question that comes up today, you'd feel really good about. Okay, and so everything that deals with complex numbers is all about this right there. The letter, well, really, the number I. But look how I wrote it. Right, I put a little tail on the end. I want you to do that as well, because if you just write an I like that, you might think of that, or I might read that as a stray mark on a piece of paper, and it really just kind of looks like a 1. So whenever you write letters, especially ones that could look like numbers, throw a little tail on the end. But what is that? What is I? Perfect. The square root of -1. And we even call that the imaginary unit, because any negative number under a square root is imaginary. So if we want just a single kind of starting point for us, we're going to call that the imaginary unit I. Okay. So if that's I, what is I squared? Right, a square is the square root. The square and the square root cancel each other out. And so we're really just left with the square root disappearing, and -1 is the only thing that's left underneath. Cool. And when we get to, and probably what you saw yesterday, is really that was the highest power we ever had to deal with, right? Because you take an I and an I, multiply them together, you get I squared, but we're going to change that every time to -1. And we're never going to leave the square root of -1. We'll always just call that I. But what, and this is what I don't think the book started to do, what if we had higher powers? Like, what if we went to I cubed? So how do you get there? So think about, like, can you use some combination of I and I squared, like put them together so that they mean I cubed? Like, how could you use the two things that we know to rewrite I cubed? But the step before that got you there. There's -1, right? There's I squared times I, when we multiply them together, we just add their coefficients, so that their exponents, that would give me 3. So really what I cubed is, right, -1 times I, which is just -I. And that's really nice that we can reduce the powers of I down to either I, -1, -I, or let's keep going. What about I to the 4th? Can you use any combination you want of any of the preceding powers to make it simpler, to reduce that power? How could you rewrite I to the 4th using any or some combination of the first 3? I squared times I squared. Nice. I squared times I squared, or I squared squared, right? -1 times -1, which is, yeah, so much nicer, right? And so what you see is that we never really need a power of I bigger than 1, and here's why. Look what happens. I to the 5th. Isn't that I to the 4th times I? And what was I to the 4th? Just 1, so we get back to I. Same thing with like I to the 6th. That's I to the 4th times I squared, which is really just 1 times I squared, which again gives me -1. I, -1, -I, 1. I, -1, -I, 1. I, -1, -I, 1. And it just goes around and around and around. I squared, I to the 3rd, I to the 4th, I to the 5th, I to the 6th, I to the 7th, I to the 8th, because you can pull out as many I to the 4ths as you've got. Now, I squared is -1, right? And I cubed is -I, and I to the 4th is really just 1, but it's got this cyclical pattern to it where we never need to leave that in order for us to be able to reduce our powers of I, because I'll make it up. I to the 22nd. If I could write this as I to some power times I to some other power, where this first one has an exponent that's a multiple of 4, then that's always going to be equal to 1. Because I to the 8th is I to the 4th times I to the 4th, which is 1 times 1, which is going to be 1. So pick a number less than or equal to 22 that is a multiple of 4. The biggest one. How about the biggest one? Yeah, 20, right? 16 works, but so does 20. Well, if I chose 20 out of the 22, how many do we have left? 2, right? But any power of I that's a multiple of 4 is always going to just give me 1. Because it's just I to the 4th times I to the 4th times I to the 4th, however many times, that's just 1. What's I squared? -1. And so we can always reduce powers of I as far down as you want to go. Okay. Do you know where I is in your calculator? Take them out. Take them out. In your calculator, There is a spot. And it's actually right on the front. It's a little sneaky. It's a little hidden somewhere. See if you can find it. Can you find the number I? Above the decimal point. Nice. Okay. Second decimal. So just right on the front, right on your main home screen there, second decimal will be I. And if you just press enter, what does it give you? I, right? It's not going to rewrite it as a square root of -1. That's like rewriting 2 squared as 2 squared instead of 4, right? But if you did something like I squared, press enter. -1, right? It's going to do all of that reduction for you, which is really, really nice. So if we did I to the 22nd, it should give us -1, and it does, okay? And so that's why I'm not going to bother testing you on reducing powers of I, because the calculator can help you do that. And I want you to rely on the technology if we've got it, okay? So I don't think the book talked much about reducing powers of I, so I wanted to make sure that I did that with you first. Cool? The other thing that I wanted to mention that I know the book talked about, but I really wanted to make it clear, is that those are just imaginary numbers, right? There's no real part to it. So when we talk about complex numbers, it's got both, the real part and the imaginary part. A plus BI, okay? And every complex number needs to be written in A plus BI form, which is called standard form, okay? And it's got a real part, the A, and an imaginary part, the BI. And that's the super fancy technical mathematical name for it, the real part and the imaginary part, okay? And sure, A might be 0. So you just have an imaginary part, it's still complex. B might be 0. So hey, maybe you just have a real number, that's still complex. Okay. But we always want to end up with that. I want to end at A plus BI. Okay, that's the goal. Now, my guess is that adding and subtracting complex numbers is pretty easy, right? Can I skip that and move on? Okay, cool. Think of I like you would X or A or B or Y or Z. Think of it like you would any other variable and treat it like that when you're adding and subtracting, right? Just worry about the coefficients and we kind of go from there. Okay. Let's get closer and a little. Whoa. Thank you for the extra hand. If anybody wants to like find me a tall, light, not quite so heavy box for me to do this, that would save me a whole lot of trouble. All right, let's skip on to multiplication. And just make sure you're cool with it. Okay, multiply. And I'm just going to make it up. I'm just going to take a couple complex numbers and let's just multiply them together. I don't know, I'm going to make it up. How about 2 plus 3i and 4 minus 6i? Okay. Well, let's see what happens when we multiply them together. And you looked at stuff like this yesterday when you're looking at example number 2, and maybe it was just like a 5 times a complex number, and okay, I'll just distribute the 5. But when we have 2 complex numbers that have non-zero values for A and B,
Mr. Rosengren?
That we distribute. Yeah, Riley, what's up?
What does that say on the board?
Multiply.
Okay.
2 plus 3i.
Okay.
And 4 minus 6i.
Okay, thank you.
Maybe if I drop this down a little bit, I'll write a little bigger too. Okay. So let's distribute, right? And FOIL, double distribute, whatever you want to call it. Draw the arcs if you like it. But really, the idea is we're just going to multiply just like we normally would anywhere. 2 times 4, okay, 8. And I like to do the first number through everything, then the second number through everything. That's just kind of the order that I go in, so I make sure I don't miss anything. So I'm going to do the 2 times the negative 6i, call it negative 12i. Oh, this kind of worked out nice. Okay, 3i times 4 plus 12i. And then 3i times negative 6i. Numbers with numbers, i's with i's. What do you end up with when you do these last two? Good. Negative 18I squared. Okay. Now, I know what I want to end up with. I want to end up with the real part first and the imaginary part second. But the thing that I think would be probably worth our while is to take a second and reduce any powers of I, because I never need anything bigger than a power of 1. It's got to be I or negative I, 1 or negative 1. So you've got this I squared. Well, what is that? Negative 1, right? And if you wanted to really take your time, you could say, okay, I've got 8 minus 12I plus 12I minus 18 times negative 1 and make that like its whole step. That seems a little slow. I think we could probably go a little bit faster and say, you know what? Way back here, negative 18I squared. If I squared is negative 1, what's going to happen to this whole term, negative 18I squared? What's that going to change into? Positive 18. So this is what I do. I circle it, and I put plus 18. This way I'm not wasting a step, wasting time, and I can start doing things a little bit faster, because now I can put all the real parts together first, then the imaginary parts. So 8 plus the 18, okay, 26. Negative 12I plus 12I. Great. Done. That's the result, and that's okay. When we multiply complex numbers together, we might not get non-zero results for A and B. We might get one or both to actually end up being 0. Let's do one that actually has some real values. 3 minus I and 4 plus, let's make sure to do it again, 5I. 3 minus I times 4 plus 5I. And you just kind of do the same thing, right? Multiply it out. We'll reduce powers of I first, then we'll start putting stuff together. So the 3 times the 4, okay, cool, 12. The 3 times the 5I, so 15I. The negative I times the 4, so minus 4I. And then negative I times positive 5I, so negative 5I squared. I always reduce my powers first, because then I'll take all my real numbers, put them together, then all my imaginary numbers, put those together. But I just go like this. I circle any power of I, along with this coefficient and the sign that goes with it. What should negative 5I squared turn into when we reduce it? We'll put a plus 5. Then I can keep going. Okay, so now I've got the 12 and the 5. Okay, so 17. 15I minus, 15I minus 4I, so 11. A plus B. Cool? Nice. All right. The stuff that really makes us think just a little bit more is the division. Okay, and that's really what I want to focus on. And if you can do everything, that means you can do division. Okay, so let's do that. Because I know what I got to end up with. I have to end as A plus BI. But if I've got, and I'm just going to make it up, 4 plus 2I over, I don't know, 2 minus 5I. Well, before we even do that, like, what if you had, I don't know, 2 plus 6 over 1 minus 4? No I's. You don't have to write this down. You can just look. How would you simplify this fraction so it's as simple as it can get? Yeah, right? Put the tops together. Put the bottoms together. And if you can simplify, you will. In this case, we can't. But does that work? Does that allow us to like divide straight down? Can I do like, okay, 2 divided by 1 plus and a minus, and then 6/4, so 3/2. Is 2 minus 1/2 negative 8/3? No way, right? And it's because you've got addition and subtraction connecting things up top. It doesn't allow you to divide straight down. So I can't just say, okay, this is 2 minus 2/5. I really wish I could, but it doesn't work out that way. And so we need a different strategy on how to get ourselves to be able to actually divide. And the problem is you've got this binomial denominator. And if it wasn't, like if this was 4 plus 2i over, not 2 minus 5i, but just 2, you can separately divide every term from the numerator, like 4 over 2 plus 2 over 2i, 2 plus I, and we'd be done, right? That would be really nice, right? Just like when we add fractions. 1/5 plus 2/5. 3/5, right? But the step in between that we never bother to write is the step that we're doing in our heads. We're adding the numerators, leaving the denominator the same. And if I can go this way, that means I can also go that way. I can break fractions apart. Two things being added or subtracted over a single denominator, I can write them separately as each fraction, right? So if we could turn this into something that looks like this, then we'll just follow that path, we'll break them apart, and we should end with a nice complex number in complex number standard form. So how do we do that? How do we get rid of that I on the bottom if you've got a binomial complex number? It's like, kind of like, I want to rationalize, but it's not irrational, it's complex, imaginary, right? I want to realize the denominator. How can we get rid of that I in the denominator? Just multiply the numerator and the denominator by the denominator. Like kind of like when we rationalize, right? You have a square root of 2 on the bottom, so you multiply top and bottom by the square root, right? Let's see what happens. Just watch if we did that. Multiply, so 2 minus 5i on top, 2 minus 5i on the bottom. Right? Kind of like what we did, we rationalized. Now remember that when we do that, when we multiply, just like we did, I'm just pulling something up for later, we just have to distribute kind of like we did over here, right? So, okay, multiply at the top. So I'm going to go quick. 8 minus 20i, pick a nicer one. 8 minus 20i plus 4i minus 10i squared, and 4 minus 10i minus 10i plus 25i squared. Look at the denominator. Sure, there's the negative 25. So that I squared is gone, but do these i's disappear? No, I'm still going to end up with a complex number that still has I in it. But it's a really good idea, right? And that's kind of like E down here, right? Take a look, right? If you look back at your results from example 2 from yesterday, we multiplied a complex number by itself, right? And what happened when we did that, so Riley can see a little bit, when we multiplied those complex numbers by themselves, we still end up with a complex number. So look back at that work from example 2. Which example, A, B, C, D, or E, got us a result that didn't have an I left over? C, right? Look at the setup for how we multiplied them together. Were they exactly the same? No, but they were darn close, right? Same number, but just opposite signs in between. That's the key for binomial denominators. Not multiplying by exactly what's there, but by multiplying by what's called the complex conjugate. Okay? The complex conjugate. Okay? C-O-N-J-U-G-A-T-E. Okay? The complex conjugate. So if you have some A plus BI, if that's your number, okay, the complex conjugate of that is A minus bi. All right, so if you start with plus, change it to a minus. If you start with a minus, let's change it to a plus. It's kind of like when we factor difference of squares, right? X plus 3, x minus 3, the x's disappear, and you just have an x squared and the 9. We're just kind of trying to undo that and picking the right pair of numbers to do what we want. And I just want those i's, not x's. I want the i's to disappear, okay? So that's the plan. So when we divide, okay, what we want to do is we want to multiply numerator and denominator by the complex conjugate of the denominator. Multiply numerator and denominator by the complex conjugate of the denominator. We want to realize the denominator because I just can't divide straight down as much as I'd like to. Multiply numerator and denominator by the complex conjugate of that denominator. And that's going to come in really handy when we get to rationals in calculus, especially with square roots. It won't be a complex conjugate, it'll be a radical conjugate. We'll just switch the sign in between. Okay, so let's do it. Let's actually multiply this out and watch the magic happen. 8 is 4 times 2. Okay, cool. So plus 20i plus 4i plus 10i squared. Got to extend my fraction bar just a little further to make sure it's covering. And then the denominator. 2 times 2 is 4. Plus 10i. Oh, there it is. Minus 10i, and they're gone. Don't forget that last one, negative 25i squared. Again, extend my fraction bar just a little further, just to make sure it's all covered. Always, always, always reduce your powers of I first. Okay, it just makes adding and subtracting everything so much easier when you've got it, right? So if I've got an I squared or an I cubed, and we really don't have to deal with anything like that, we just have our I squareds right down and right there. So positive 10i squared, what is that going to change to? Negative 10. And then on the bottom, positive 25. And I just write it like that. You can write it however you want. That's just the style that I'm cool with and the way that I like to do it. Real parts together, imaginary parts together. So real parts first. Okay, so negative 2 plus 24i. There's my numerator. And then on the bottom, real parts first. I made this problem up, so that's why it's not going to work out all that nice. But 29 plus 10i minus 10i gone. And now we've got a problem that looks like this one, which means we can keep going. Single monomial denominator means everything from the top can get divided by 29. So I've got this negative 2 over 29. Pull the negative out front because the number is negative. That number just happens to be a fraction. Plus, now a plus bi, where the b and the I are separate, okay? Take the 24 and the 29, the numbers, and pull that fraction out and put the I next to it. Okay, a plus bi, done. If we could simplify either of those fractions, we would, of course. Just like you kind of did with example 4, you had like 2 over 20, right? And then 16 over 20, so 1/10 and 4/5. We can make that a little bit simpler. Okay, so reduce your powers of I, and then simplify. Okay, a plus bi is what we know we got to end up with. Okay, that's really the only one that takes any thinking, any process. Okay, but now that we can do that, now we can do things we weren't able to do before that. This is the last thing that I'll touch on, and then I will give you a chance to just start and finish your homework right now. Let's try to solve x squared plus 4 equals 0. How many x's are in that problem? Then go get it, right? Don't factor, don't quadratic formula. If you have a single x in a problem and you're just asked to solve, just go find it. So what should we do first? Subtract 4, right? Minus 4, cool, gone. X squared equals negative 4. All right, I've got an x squared. I want to undo that. Square root both sides. Now, remember, when we take the square root, plus or minus, right? Any even root needs a plus or minus to go with it, okay? And it's the square root of negative 4. But I want to make that as simple as I can. So let's think about it. What's the square root of 4? Okay, cool. And so when we talk about the square root of negative 4, what I want you to kind of consider is what happens. I'm just going to drop this down so you guys can see a little bit better. What happens if, like, what do you think? The square root of 2 times the square root of 3. You're probably right. What do you think it's probably going to be? Square root of 6. And you're not wrong, right? If you've got the same root, so square roots and square roots, you can just multiply the radicands together. Cool, square root of 6. Math is a two-way street, though. If I can go this way, I can go this way. I can break radicals apart. And so what I'm going to do is I'm going to pull out the positive part of that radicand. Just the 4. What's left? What's the square root of 4? What's the square root of negative 1? So really what we end up with is plus or minus 2i. And really all you have to do is notice, if you have a negative under your square root, pull it out, call it I, and deal with every other part of that problem. Okay? So if you've got like, I don't know, that might be tough to see. I'm gonna do my best for you, Riley. I'm gonna talk through it. The square root of negative 21. Break it up into the positive part of that number and just pull out the negative 1. Is that a perfect square root of 21? Is there a perfect square factor of 21? Okay, so the square root of 21i. Now, what I want you to do and be careful of, there is a pretty clear gap between where the square root, the radical, ends and where the I begins. I don't want anybody that's reading this to think that that I is under the square. So I try to keep them close, but not too close. I put a finger width gap in between, so I'm safe. Cool? But what about something like the square root of negative 20? Right? Break that up, right? 20 and negative 1. Is that a perfect square? Is there a perfect square factor of 21? So we still have to simplify the square root of 20, right? Square root of 4, square root of 5. Square root of 4 is 2. Radical 5. Okay, and you can see visible gap between where the radical ends and where the I begins. Oh, there's the red part. Found it. Cool. There's 2.4. Done. Okay, we got about 15 minutes, so I'm going to pull up a copy of the textbook so you can see, and I'm just going to let you know which problems to do. And we'll call it homework 2.4. You can submit it, and I mean, realistically, it shouldn't take you very long because this stuff can happen so quickly. Let's see if I got it somewhere. Maybe. It should be just in my recent. Let's go there. Chapter 2. Okay, cool. So in 2.4, let's see if I can guess my way to how far down it is. Oh, multiplying conjugates, that's pretty close. Okay, cool. Let me blow this up a little bit. I'm going to pull it up for you, Riley, in just a second. I got to go a little bit higher. Okay, we are going to do And you can just kind of continue your notes. You can start on a fresh page if you want. We are going to do 21. I'm going to write it down so you don't have to write this down. But start with number 21. I got you, Riley, in just 1 sec. Just give me a second, girl. $21, $25. Hold on. Too close. I gotta back up. Of course, I had to leak on another page. Here we go. Let's do it like this. 21, 25. I need that thing at the bottom to disappear. There we go. 33, 34. I can read it too if you need it. And 35. And then I think it was 53 and 55. Okay. So just a couple adding, subtracting, a couple multiplying, and a couple dividing. Okay. Riley, I got you. And it's sitting right there on the homework assignment as well. But it is 21. 25, 33, 34, 35, 53, and 55. And I'll write some answers down so you can make sure you're doing well. And you've got a little more than 10 minutes left. I think you can probably do it. Real part first, imaginary part second. Hopefully you can see a little bit. If you need me to read you something, let me know. Yeah, Riley, go ahead.
The book went away.
You're right. There you go.
Thank you.
You're welcome. And down. There you go. I mean, realistically, if you can divide, you probably had to add, subtract, and multiply to get there. So I think on the college algebra final, they do a little bit of everything. But for me, if you can do 53 and 55, you can do all of it. So. Okay, when you're done, take a picture, put it on Canvas for me. Homework 2.4. But hopefully that was a nice little refresher for you from last year, because I know you saw it kind of towards the end, right before spring break. And one day, done, perfect. No shave till November update. We're in a close third place. 6 is kind of pulling away a little bit, more than $1.50 ahead of us right now per person. But we are less than $25 away from me dyeing my hair. So I think we're going to get there. We still have a couple weeks left. So, but you guys definitely still have a shot at deciding how ridiculous this beard is going to look. But it is looking real good. It is coming in real nice. That 10 days of fall break, I knew I was going to come back and be able to show it off a little bit. So this is the longest it's ever been. I've never had a beard this long before. And if you win and you say, you know what, Rosie, keep it through Christmas, I might just do that. I don't know if my wife would be too happy about it, but that's okay. You guys deserve it. So it's a sad state of affairs. I don't even want to look at it. Slackers. I know. What can I do? Second period is not far ahead in my mind of third period. But you guys are doing awesome. But yeah, sixth period, another $30 yesterday. $30 yesterday. So, and seventh period getting a couple too. So, the Venmo's there. The jar is here if you ever want to drop anything in. And again, I mean, I put in those grades for the test, and they went in general pretty well. But if you want to sit down and talk through it, I put the comments on Canvas, right? Hopefully you saw where you lost your points, and maybe you can figure it out from there. But if you want to sit down in person, virtually, or just kind of message each other back and forth, I'm happy to do that. I want you to know what you did well and what you need to improve on, because all this stuff is coming back on the final. So I'd hate for you to make the same mistakes, like not labeling your axes, not You know, not writing down all of the parts of the intermediate value theorem, not saying that there doesn't exist a zero instead of I cannot prove the existence of a zero. People lost points on that. Factoring was surprisingly disappointing. A lot of people lost more points than I expected on the factoring for question 7. So you might want to go back and make sure you're good with that, because we're going to need to factor tomorrow, right? So join me live tomorrow, either 2nd or 4th. I'll live stream both, so we can start 2.5 all together. But you won't have any work you'll need to do. It'll just be join me for the hour or so, a little less, because reading about something like that is not going to be nearly as effective. Okay. But finish these 1, 2, 3, 4, 7 up. Put them on Canvas so I can give you the credit for it for the day. Nice little 5 out of 5, and then we'll get started on. It's not that it's difficult. It's just there's lots of parts to it. There's lots of different things that you already know how to do. We just have to put it all together for rational functions. Because we're going to sketch these by hand. We're going to look at these and just sketch them without a calculator. So I want you to feel good about that. Okay. Cool. All set, Riley. Thank you, Riley. Okay, I'm going to stop recording because we're good. Riley, you are good. Thank you for joining us, and I will see you on Thursday.
Okay.
Welcome back.
Bye.